You may remember from the previous video, I talked about a machine learning approach to finding the best fit regression line. I described it as a sort of a try until you get to a point where loss is minimized method, but it's not a mindless trial and error. There's a more elegant way, and it's called gradient descent. It's still a little bit of a guessing game, but it's much more systemized. But before we get there, let me talk about the loss function first, because we need to understand the foundational relationship between a function and its loss very clearly. Here's a linear model, y equals mx plus b, which you probably remember from basic algebra. We'll write this in a slightly different way. Here, w0 or w0 is basically the same as b, or the intercept, and w1, x, is mx, or the slope, w1 multiplied by the value of x. And let's also write the loss function. As I've described in my previous video, loss is basically a calculation involving the predicted minus the actual. Writing it in the same notation as the linear model, we can rewrite that as this loss function. Now we'll take a look at how the loss function looks like as we experiment with the linear model. To demonstrate, I've brought a much simpler looking data that has a similar set of data points. The intercept is at 50, and we'll only mess with the slope for our purposes. The red line you see in the left chart is the linear fit when the slope is at -1. Why -1? It's just an arbitrary point that'll help us get started. You can immediately tell that the red line does an absolutely terrible job at fitting the data points. Correspondingly, the loss that is shown on the right as a single data point is calculated using the predicted points from the red line and the actual blue points. Loss is very high at 361, but watch what happens when I change the slope of the linear model. Now the slope is at -0.57, which is still pretty darn bad, but the loss has decreased to a much lower level of 272 compared to 361 that we saw before. This just means that this red line is that much closer to representing the blue points than the previous red line. Let's continue to increase the W little by little. As we get to a place where visibly the line looks closer to being the best fit line, the loss approaches a plateau, and in this example, loss seems to be pretty low. By this point, the red line does a good enough job of representing the blue points. And then, we see that as slope increases beyond the data points, loss increases back again. You're seeing that by now, the loss function is making a curve, but not just a curve, a parabola. And if you remember a thing about parabolas, it's that they have what's called a minimum, or the lowest point in the parabola. This is where the loss is nearest to the minimum. And this parabola shape is made because our function has a square term, which makes it very easy for us to spot the minimum point. Actually, it's not technically the lowest point because we have been hopping through different slopes instead of checking every possible value, but it'll be very close to being at the minimum. So we have a way of estimating the best fit line by looking at where the loss curve is minimized. But one challenge that you might have noticed is that in order to find this minimum point, we pretty much had to evaluate a bunch of points by trying different values of W. And I told you that it's not going to be just a guessing game, because that would be very inefficient. So how can we do this in a more efficient way? Enter gradient descent. Gradient descent does the same exercise that we did, but in a much more efficient way. Let's take a look at this familiar shaped loss curve again. Our objective is to find W that minimizes JW, or the loss. And again, we can't just look at this curve and know where W is minimized, because remember that the act of creating this curve in the first place requires a computation that exhaustively goes through every single value of W, which can theoretically be an infinite number of calculations. So just imagine that this black line and the red point isn't visible. How the heck does gradient descent allow us to find the minimum efficiently? The gradient descent algorithm will work as follows. Initially, some value of W will be chosen at random. Suppose it chose this point on the parabola as its initial value. Now, it asks itself, do I need to go up or down to reach a point where the slope is near 0? It figures this out by only looking at the gradient, or the slope. If the slope is positive, as it is right here, then W should go down. If the gradient is negative, then W should go up. And steeper the gradient, the further away from the minimum it is, so W must take a larger step. And flatter the gradient, closer it is to the minimum, so W should take a smaller step. And W keeps updating itself following this rule until it gets to a certain point where there is only a tiny unnoticeable amount of movement. This is what we call the point of convergence. So gradient descent is an algorithm where the weight W can update itself to find where JW is minimized. And by looking at this particular graph, it went pretty close to the minimum in just 4 steps, which is much less steps than trying to plot out many values of JW as we have done before. There's another factor in the gradient descent algorithm called the learning rate, shown by the alpha symbol in this equation. The learning rate determines how aggressive or conservative it should be in changing W. The learning rate is a hyperparameter, which means that it's up to the modeler's decision to decide how big or how small this number should be. Remember how I said machine learning is just as much art as it is science? Here's another example of that. As the person building the model, you need to choose the learning rate carefully. The good news is, you'll be able to experiment with it and tweak the rate to see how the model performs with your data. If the learning rate is too large, then it takes too big of a step, and it might even surpass the minimum. And when it goes back in the other direction, it can take an even bigger step backwards, and so forth. We call this divergence. And if the learning rate is too small, it'll move too slowly, which defeats the purpose of it being an efficient algorithm. This is the most fundamental algorithm used to find loss to train a machine learning model. Every time a model goes through the data, or in technical terms, for every epoch, it'll do a gradient descent to find the loss, and then update the model parameters based on it. And over time, loss will have reached a low point, and the machine may have improved or learned how to make a prediction. However, in practice, gradient descent isn't performed as is. There are some deviations from it that makes them even more efficient. Gradient descent uses all data points to compute the gradient and find the loss. So by going through all the data, it becomes slow. It calculates a precise estimate of the gradient, but it turns out we don't really need to be that precise. Stochastic gradient descent, instead of using all data, it picks and uses only one random data point each time you estimate the gradient. You'll guess this is several degrees faster, but it makes the estimate a bit noisy and less precise. Instead, the widely used method is the mini-batch stochastic gradient descent. It's a mouthful. When people refer to gradient descent or stochastic gradient descent or SGD, they probably mean a mini-batch stochastic gradient descent. This is when only small random batches of the dataset is used to calculate the gradient. The idea is, if you have good data, then one small subset of the data should be similar to another random batch of the data. So there's no reason why we should be using all data points. And for each new epoch, a new random batch is chosen. Here, both batch size and epoch are other hyperparameters, so these can be played around with. All in all, SGD is an optimizer. Optimizers are algorithms that are used to minimize error. And there are different types of optimizers, SGD being one of them. At this point, I haven't decided whether I want to spend time making videos on different optimizers, but for now, just know that they all work in a similar manner as the SGD. When building a model, you will likely need to choose between different options for optimizers. SGD will be a fairly standard choice in many situations, but you might choose others like Atom, Attograd, or RMSProp, depending on what model you're building. As I keep reiterating, machine learning is a bunch of choices you have to make, and there are a lot of steps involved in building and using a model. Choosing an optimizer is just one of the things that you will need to think about when building a model. If you haven't subscribed to the channel yet, please do so because we're going to cover all the steps in a practical machine learning model building flow in our next video.